with us as well. All right. I hope that's fine for you. So we'll start with the session. Yeah. So the first question says, for a given input vector tau, this is a Greek symbol tau, calculate the resulting motion of the robot, that is eta dot is not, is known as, do you know the answer of this question? See, if you are given
forward kinematics.
Forward dynamics.
No, kinematics.
Kinematics. So what is the difference between dynamics and kinematics?
Dynamics is kind of like the math which we learn in 10th class. Like I can't tell that.
Yeah. So in this regard, the kinematics only deals with the motion. It doesn't cover what causes the motion. And dynamics also covers the effect or what causes the motion. So it will take into account as well. So kinematics basically deals with this expression. Eta dot would be Jacobian times J of psi times theta. Where dynamics, you will deal with equation of motion, where tau would be the torque vector. This would be d times of zeta dot plus n of zeta. So kinematics only deals with motion. It doesn't cover what causes the motion. It doesn't really concern about what causes the motion. Whereas in case of dynamics, it covers it covers the cause of motion, which are usually the forces. So what causes acceleration? The forces acting on it, and any unbalanced force acting on a rigid body would cause an acceleration along the direction of force. So it will also, apart from the motion, it will also take care of what causes the motion as well. So in case of the question, clearly a torque vector is involved. So it's definitely a case of dynamics. So we need to see what would that be, whether it is forward dynamics or inverse dynamics problem. So I hope this is a straightforward question. So if you have a robotic system, if you are supplying the torque vector and you are finding the trajectory of the robot, the trajectory would be defined in terms of its acceleration, velocities, and positions. And its positions. So if the torque vector is given, the time response of torque is given, finding out the trajectory is what we call the forward problem or the forward dynamics. Whereas in case of the reverse problem, in case if you are given the trajectory and you are asked to find out what would be the torque vector acting on all the joint variables, this would be the inverse kinematics problem. Sorry, inverse dynamics. Inverse dynamics problem. So the question clearly asks, you are given a torque vector, you are supposed to find out what are the trajectory of the robot. So in this regard, the correct answer would be forward dynamics. I hope this is clear. This is a straightforward definition of what the dynamics is. It's forward dynamics means finding out the trajectory given the torque vector, and inverse dynamics would be finding out the torque vector given the trajectory. Yeah. So yeah, moving on to the second question. It says the Lagrangian is equal to. So these would be the typical sort of questions that you can expect during your assignments as well as your final quizzes. So if you can clear out, if you can clear these sort of questions, you'll be fine with respect to your end week assignments as well as end semester courses. So again, this is also a straightforward definition. Lagrangian, all the options correct. For the first option says whether Lagrangian is equal to kinetic energy plus potential energy. The second option says kinetic energy minus potential energy. Third option is a product of both of these kinetic and potential energies. and all the remaining options are basically irrelevant. As per the definition, it should be evident that Lagrangian would be kinetic energy minus potential energy. And where would you use this Lagrangian? You would use this Lagrangian to derive the equations of motion of a robotic manipulator. So you would use the Lagrangian to find out these equations of motion of a robotic system. Where you would use the Lagrangian this would correspond to the equations of motion of a robotic system. And as per the definition, Lagrangian is simply the difference of kinetic energy minus potential, difference of kinetic and potential energies. So in case of a land-based mobile robot, what would be the Lagrangian? Because if you consider a land-based mobile robot, it will operate or it will live only along a plane. So if you consider this plane as a datum, or the reference where the potential energy is zero, the potential energy would be zero throughout or constant throughout this entire datum. So in that case, you can consider potential energy to be zero in case of a land-based mobile robot. But in case of a general robotic system, maybe in case of a spatial robotic manipulator or in case of underwater vehicles, Lagrangian is defined to be the difference between kinetic and potential energies. So I hope that is clear as well. Yeah, so the option says kinetic and potential. The correct option is option B, kinetic energy minus potential energy. Yeah. So moving on to the third problem, it says a given differential wheel mobile robot, if the first wheel is generating a traction force of 1 newtons and the second wheel is also generating a traction force of 2 newtons, then what will be the forward and lateral direction forces? So if you can recall, a differential wheel robot would be of this configuration. The robot chassis along with 2 wheels driven independently. And what I'm drawing over here is the body fixed frame. And throughout these assignments, maybe during this in the course of this tutorial, as well as the questions that you'd be solving, you would see some references in the questions. So if this is a standard schematic of a differential robot, this would be your left side and this would be your right side. And along the x-axis is what we call the longitudinal direction, and perpendicular to that along the plane is your lateral direction. Again, it says your the first wheel or the left wheel is generating a traction force of 1 newtons, and your right wheel is generating a traction force of 2 newtons. Yeah, then what will be the forward and lateral direction forces? All right, so basically you are given the force vectors along the wheel. You are required to find the mapping between the wheel forces or the traction forces to the body fixed reference frame. You have to find a mapping. So how to do that? So if you simply do the balancing of forces, the force along this x-axis, sigma fx, would be the force on the left wheel, sum of force on the left wheel and force on the right wheel. So in this regard, as per the question, the forces acting on x-axis would be 1 plus 2, this would be 3 newtons. And if you're using the force balance on the lateral direction, sigma Fy would be 0, right? Because there are no forces, no components of forces acting along the lateral direction. So yeah, forces, force along the forward direction or the lateral direction would be, force along the longitudinal direction is 3 newtons. and the force along the lateral direction is 0 newtons. So in that regard, what is the correct option? Option 3 says 3 newtons and 0 newtons. Option C. Right? Because for a differential wheel, the forces, the traction forces can act only along the one direction. That would be perpendicular to the wheel hub or the direction, the plane at which the wheels would be rotating. So if you simply resolve the forces along the body fixed frame of reference, you would get the longitudinal forces. The sum of the total longitudinal forces would be 3 newtons, and the forces along the lateral directions would be 0 newtons. So I hope that is clear. Yeah. Murali, I hope it's fine if you can hear me. Okay.
Yeah, it's fine.
Okay. Thank you.
It's just that thinking a little bit forward. That's the only thing.
Yeah. All right. Yeah.
But I mean, let's go.
Okay. So moving on to the next problem, it is also something related to differential wheel mobile robot. So yeah, in a given differential wheel mobile robot, if the first wheel is generating a traction force of 1 Newton and the second or the right wheel is generating a traction force of 2 Newtons, then what will be the vehicle motion? So again, based on intuition, it will be fairly straightforward to see in what direction the robot would be moving. This is the body fixed frame, x-axis, y-axis. The left wheel is generating a force of 1 Newton and the right wheel is generating a force of 2 Newtons. So again, based on your intuition, what direction would be the robot moving? It will have a forward component. And since the right wheel exerts more torque than the left wheel or more force than the left wheel, the robot will also have a tendency to rotate in the counterclockwise sense also. So if this is your inertial frame of reference, and if the robot at time t equal to 0 is at this point, at this origin, it will move in this fashion. It will move straight and it will also have a component along the counterclockwise direction. So this is based on intuition. Just intuitively, this would be this would be how the motion would look like. So it will move forward and also it will rotate in a counterclockwise direction. Option C. But again, if you want the formal proof, if you resolve all the forces along x, y, and the moments, sigma fx, the forces along x-axis would be FL plus FR. Force on left wheel, this would be FL, this would be FR. So this would be 3 newtons. And the force along the y-axis, sigma Fy would be 0 newtons. And if you resolve the moment about the z-axis, what would be the moment? So if I am taking, yeah, the length or the width of the robot as 2D, and from the origin, it's simply D. This would be D and this would be D. So if you resolve the moments along the z-axis, it would be simply minus 1 newtons times D plus 2 newtons times D. So this would be simply D. So the robot will have a forward component. It will have a forward component of 3 newtons. It does not have any lateral component. And it also has a positive counterclockwise component. It will also have a moment about the z-axis. Since the sign is positive, it will also have a counterclockwise rotation. So again, it is in line with our intuition also. Without doing any numerical analysis, we have already zeroed upon option 3. Numerical analysis also basically confirms our intuition. So we'll go ahead with option 3, option C, moving forward and rotate in counterclockwise direction. All right. Yeah. That is correct, I suppose. Yes. Yeah, moving to Did we discuss these questions? Okay. Question 3 we have discussed, I suppose. Yeah. Question 4 we have discussed. Question 5. So the configuration changes. So it says for a mechanism wheel drive, the wheel configuration matrix in dynamic level can be written as so and so. So if the vehicle needs to move in a lateral direction towards right, then what would be the individual wheel forces? So if you can recall from the course, I'll reproduce the configuration of the mechanism wheel. I hope it is. Yeah. So the mechanism wheel will have passive rollers along. For the first wheel, it will have passive rollers along this direction. First and third will have the same direction of passive rollers. And second and fourth will have a different direction of passive rollers. We'll also have a body fixed frame, x-axis, y-axis, and also the z-axis. So this would correspond to the left side, and this would correspond to the right side. This would be the longitudinal direction, and this would be the lateral direction. All right. So yeah, 1 second. Yeah. So the dynamic transformation matrix given in this problem corresponds to a mechanism wheel of this configuration, of this wheel configuration. So our requirement is to make the robot move along the lateral direction. So if the robot is to move along a lateral direction, purely in a lateral direction, how would the force matrix, how would this matrix look like? If the robot is to move along a lateral direction, that too towards the right direction, it should look like this, right? The force vector should be of this form. It should have 0 component along x-axis. It should have a negative k or a constant in the negative y direction, because that corresponds to the right direction of the robot. And it should have 0 component along the z-axis also, because the robot should be moving strictly along the negative lateral direction or the negative y-axis. So if this is our requirement, then what would be the right combination of forces? So we'll go through the cases. So if I'm reproducing the configuration matrix over here, 1 by root 2 times 1, 1, 1, 1, 1 minus 1, 1 minus 1, L minus D, L minus D, minus L minus D, minus of L minus D. So we'll go through the cases. So again, I'm rewriting our requirement. It should look like this. The force vector should look somewhat like this. The left hand side of this equation should look like this. So we should find what would be the right combination of forces, individual wheel forces, so that we can achieve the left hand side. So what about the first case? So the first case says all the 4 forces along all the 4 wheels should be positive, should be of equal magnitude, and also should be positive F. So purely going by the intuition, that should not be the case, right? Because if all the 4 forces are positive, the robot will only move in a forward direction, right? Then what about the second option? The first 2 forces are positive Fs, and third and fourth would be same magnitude but in opposite direction. It will be of this configuration: positive F, negative F, negative F. So would this be the case? So what happens if we simply multiply this matrix throughout? So the first row would be F plus F plus F plus F. It would be a 4F. Second row would be F minus F plus F minus F. And the third row would be F times L minus D plus F times L minus D plus F times L minus D plus F times L minus D. So this in turn would look like 4F 0 4F times L minus D. So obviously this is not the form that we are looking for. We would only want our forces, only want a component in the second row or along the Fy direction. So option 3 is not of the right choice. That is obviously not the right choice. Then what would be the next option? What would be option 4? It says plus F minus F plus F minus F. Yeah, option 4 would be plus F minus F plus F minus F. We'll see if this is the correct answer. So if you simply multiply this matrix through, so the first row would be F minus F plus F minus F. The second row would be F plus F plus F plus F. The third row would be F times L minus D minus F times L minus D minus F times L minus D plus F times L minus D. So on simplifying, this would look like 0, 4F, 0. So again, if you compare the left-hand side and right-hand side, this is exactly how we want our force vector to be. So in that regard, we can confidently say that option 4 is the right answer. Sorry, option 3, right? Minus F, or is it option 4? Note that as per our matrix multiplication, the y component is positive. It says a 4F component. So the robot will move along positive y direction, but that is not we wanted. According to the question, we want the robot to move in the negative y axis. So we would expect a negative component here. So we would simply invert the signs that we are using. We are currently evaluating the third option. So if we are inverting this option, inverting the signs, so rather than plus F minus F plus F minus F, if we invert the sign, the robot will move in the opposite direction, right? So I think we were evaluating the fourth option, and the option that corresponds to the inverted sign would be option 3, option C. So the right answer would be minus F plus F minus F plus F. So if you multiply this out, you will end up with a negative sign here. So that is exactly how we want our force vector to be. So in that regard, our correct option would be option C. Minus F plus F minus F plus F. The first wheel should be minus F. The second individual wheel force should be positive F. The third should be negative F, and the fourth should be positive F. So I hope that is clear as well. Option C, yes. Yeah. And again, this is a similar question that too corresponds to mechanism wheel drive. So yeah, again, the wheel configuration matrix is given. And the question now says, if the vehicle needs to rotate in a clockwise direction on its own position, then what would be the individual wheel forces? So if this is the mechanism wheel chassis, and if this is the body fixed frame, x-axis, y-axis, we would want the robot to rotate about its own axis in the clockwise sense. All right. So how would we want our left hand side of this equation to be? So we would want our left hand side, the force vector, to be 0 component along x-axis, 0 component along y-axis, and a negative constant along z-axis. Because the rotate is rotating in a clockwise direction, so we would have a negative sign. If the robot is rotating counterclockwise, we would have a positive sign. Right. So what would be the correct choice? Again, if I'm recreating the right hand side here, 1 by root 2 times 1, 1, 1, 1. The second row would be 1, minus 1, 1, minus 1. Third row would be L minus D, L minus D, minus L minus D, minus L minus D. So again, if we are going through the first option, we have already ruled out that all forces being positive and equal will only result the robot to move along the longitudinal direction. So we'll rule out the first option. And what about the second option? Plus F, minus F, minus F. So that seems interesting. So the first one side would be plus F. Sorry. It says the forces along one plane or one side would be in one direction, and the other side would be in the opposite direction. We'll see if this is the case. So yeah, option 2 says first wheel force would be plus F, second also plus F, third would be minus F, fourth would be minus F. So if we simply multiply this one out, what would we get? 1 by root 2 times F plus F minus F minus F. Second row would be F minus F minus F plus F. The third row would be F times L minus D plus F times L minus D plus F times L minus D plus F times L minus D. So on simplifying, this would result in 1 by root 2 times 0, 0, 4F times L minus D. So again, on comparing with our requirement, this is almost equal, but we also wanted a negative sign also. So obviously, in our case, the third term, the non-zero term, would be positive if L is greater than D, where 2 times L would be the length of the base, and 2 times D would be the breadth. Or in other terms, you can also say 2 times L would be the wheelbase and 2 times D would be the track of the base. So in this obvious, most probably, like if the question does not explicitly states what is greater, you can always consider L to be greater than D. So if L is greater than D, obviously this would be a positive. The third entry would be, the third component would always be a positive component, but we would want a negative component along the third negative. We would want the third component to be negative. So our option 2 says plus F, minus F, minus F. So if we simply invert, or if we simply flip the direction of the individual wheel forces, the robot will move in the opposite direction as well. Right. So we'll see if that is correct or not. So if I am simply inverting the forces, so if I'm inverting the forces, the first 2 forces would be negative F and the third and fourth would be positive F. So if I'm multiplying this out, we would end up with minus F plus F plus F. And the second row would be minus F plus F minus F. The third row would be minus F times L minus D minus F times L minus D plus, sorry, again, minus f times L minus D minus f times L minus D. So on simplifying, this would yield 1 by root 2 times 0, 0 minus 4 f times L minus D. So again, this is exactly how we want it. We would want a negative constant along the third component. This is exactly as per our requirement. So this option corresponds to the answer that we are looking for. First two forces being negative and the third and fourth forces being positive. So which option corresponds to this answer? First two being negative and third and fourth being positive. I think option E, right? This option corresponds to the answer that we are looking for. So in that regard, I hope we can all agree that option E is correct. Right?
So clarification is it?
Yeah. Any questions?
Yeah.
Yeah.
So clarification. So this option which you selected is mathematically correct in terms of producing the dot vector.
Yeah, exactly. Yeah.
But if you see intuition wise,
Yeah.
so if I apply that minus f to the left is plus f to the right, so do you think the robot will turn clockwise?
Yeah, exactly. Intuition wise, if you want the robot to move in clockwise sense, you would want, as per the correct answer, this is how the forces would look like, right? And if this is how the forces are applied, intuitively the robot should move counterclockwise direction, right? I suppose that is your question, right, Murali? Yeah. But it should be exactly opposite if the robot should be moving in a clockwise direction. So the reason is the reason would be how we actually have these the roller direction, I think. See, as per our convention, how we derived this configuration matrix, the roller of the first wheel would be in this axis, would be in this direction. First and third wheel would be in this inclination, and second and fourth would be in this opposite direction. So if we flip this orientation, I suppose it'll most probably match with our intuition in that regard.
Okay.
Right. And this thing is not as per our intuition. Like if the motion is purely differential, then what you said is right. If the motion is purely differential, it should be moving clockwise or counterclockwise depending on the forces that we apply. But in this particular case of mechanism wheels, it's not as per our intuition. So we can easily get fooled regarding the direction of rotation. So we'll have to carefully go through these options to see in what direction the robot would actually move. So based on this thing, intuitively the robot should move in a counterclockwise direction. But if you substitute all the force vectors on the configuration matrix, you would see that the robot would actually move in clockwise sense.
So configuration matrix is the right one for this robot, right?
Yeah, for this robot, for this configuration, this would be the configuration matrix. And if you flip the wheel position, if you feel the wheel rollers, instead of removing this, I'll again redraw this. Maybe if the rollers are aligned in some other fashion, maybe something like this, we'll end up with a different configuration matrix. But in the lectures for the dynamic modeling, for the lectures, we have been using this case for the lectures. We need to see what will happen if you are using this configuration. We'll end up with a different configuration matrix. Okay. Shall we move on to the next question?
Yeah, sure.
Okay.
Thank you.
Thank you. All right. So question 7 says you are given a matrix, that too a rectangular matrix. So what will be the Moore-Penrose pseudo inverse of A? So could you identify how? Could any one of you identify what would be the right solution of Moore-Penrose inverse for this equation? So there are two cases of Moore-Penrose inverse. That depends on what sort of matrix that you are dealing with. So I'll explain the case specific to these sort of matrix where the number of rows are less than the number of columns, or number of equations less than number of unknowns. So for a typical system of linear equations of this form, Ax equal to b, so the number of equations less than the number of unknowns would mean the system is underdetermined. So this would basically mean the system or the vector x has infinite solutions. X will have infinite solutions, right? So how do you find out what the particular x? So if you want to find a solution, x would be in terms of A inverse B. But A inverse wouldn't exist for a rectangular matrix. It would only exist for a square matrix. So in case of a rectangular matrix, you would have a concept called a pseudo inverse, A pseudo inverse B. This would give you the solution of x. But from out of all these infinite solutions, what solution would you select? So most typically we would select a solution that has the minimum norm. We would, for an underdetermined solutions, for an underdetermined set, underdetermined system of equations, we would use x that has minimal norm. What basically the minimum norm means the length of the vector x should be minimum. The solution that has minimal length, that out of all this infinite solution, we would typically go with the solution that has the minimal norm. So this is exclusive for this underdetermined solutions. In case of overdetermined solutions, we'll never have a solution. We'll never have an exact solution. We'll go ahead with the approximate solution that will have the minimal least square error with respect to this actual solution. But for an underdetermined solution, the question clearly says it is from the question, it is clear that the system is underdetermined. It will have infinite set of solutions. So in that case, we'll go ahead with this minimal norm solution. So this would basically call for an optimization routine where our objective function would be, we would simply minimize this objective function f subjected to some constraints. Such the constraints would be ax times b. So we would want to find out a vector x of minimal norm such that ax minus b would be satisfied. For example, see if the set of equations would be ax equal to b. In this case, A would be a 3x4 matrix, X would be a 4x1 vector, B would be a 3x1 vector. So our optimization would require us to minimize this objective function, minimize x such that ax minus b is satisfied, or ax subjected to the constraints ax minus b, where lambda is something what we call Lagrange multipliers. So if you are minimizing something subjected to some constraints, you will have Lagrangian multipliers. This is basically a standard Lagrangian multiplier minimization problem. So in other words, you can simply write this scalar equation in terms of this one. X transpose X. X transpose X is basically it's the dot product of matrix X onto itself plus lambda times AX minus B. Lambda transpose times AX minus B. So we would differentiate this F in order for us to find out the minimal solution of X, the solution of X that would minimize this objective function. We would first differentiate this objective function in terms of X. Dou F by dou X would be 2 times X plus what would be the differential partial derivative of lambda times X minus B. So X would get cancelled. You will end up with terms A and lambda. But in order for us to make the units consistent, X is simply a 4 cross 1 vector. A is a 3 cross 4 matrix, and lambda is a 4 cross 1 vector again. So in order for us to make the dimensions consistent, this has to be A transpose. This would be A transpose lambda. So if you are equating this to 0, from equation 1, what would be the value of X? X would simply be minus A transpose lambda by 2. So let this be our equation 2. And again, if you are differentiating this Lagrangian, the objective function with respect to lambda, dou F by dou lambda, this would in turn we would end up with AX minus B equals 0. This would be equation 3. So if you're substituting X from equation 2, if you're substituting equation 2 in equation 3, we would get minus A transpose, you would get minus A transpose lambda by 2. This would be equal to B. So what would be lambda? Lambda would be minus A transpose. Lambda would be A transpose, the whole inverse times 2B. A minus sign will also be there. This is equation 4. So if you're substituting this equation 4 back into equation 2, so 4 into would give you the value of X. X would be minus A transpose, lambda would be minus A transpose inverse 2B by 2. So this would be, so what would be your X? The final expression of X would be A transpose A transpose whole inverse B. This would be the final expression of X. X in the sense the minimal norm final solution of X. So this would correspond to out of all these infinite solutions, this solution would correspond to the minimal norm solution. And over here is what you have a pseudo inverse. Or in this regard, for underdetermined systems, you would have something called right pseudo inverse. Right. So based on the minimal norm approximation, your right pseudo inverse is A transpose A transpose whole inverse. This is your right pseudo inverse as per the minimal norm optimization. All right. So yeah, in this regard, you are given a matrix A. So to find out this minimal norm solution or the Moore pseudo inverse, according to the minimal norm approximation, your answer you have to first find out. You have to find out A transpose A transpose, then whole inverse, then pre-multiplied with A transpose. So if you do out this math completely, your correct answer would be the right answer should be, I guess, option A. Right. Whereas in case of an overdetermined system, it will be exactly opposite. So this is applicable for underdetermined systems. Whereas in case of overdetermined system, you will have a different set of optimization, based on least square optimization. Then you will end up with the left pseudo inverse. But for a right pseudo inverse, for an underdetermined system, this is what the final solution would be. So yeah, I think let's check the solution. Yeah, as per the solution manual, this is the correct option. How did we find out? The solution we found out is using this pseudo inverse A transpose A transpose the whole inverse. Yeah, I hope this is clear enough. Yeah. We'll move on to question 8. Right. So we have been given. I hope there are no questions regarding the previous problem. Right.
No questions.
Okay. Yeah. So we'll go with the question 8. So we have been given an inertia matrix of a mobile robot with respect to its body frame. So if the vehicle orientation is 60 degrees with respect to inertial frame, then what will be the inertial matrix? What will be the inertia matrix with respect to the inertial frame? So let this be your inertial frame of reference. Fix it to the ground, X and Y. And it, as per the question, it says our robot is oriented at 60 degrees with respect to the inertial frame of reference. And let this be the body fixed frame, X and Y. So the orientation is 60 degrees. We have also been given an inertia matrix with respect to the body frame. This is with respect to the body frame. Body frame B. And we are asked to find out the inertial matrix, the inertia matrix or the mass matrix with respect to the inertial frame. So how do we do that? So if you know the formula by heart, you can do that. But again, the derivation is also quite straightforward. So yeah, first of all, we'll start with the kinematics. So in the kinematics level, we'll deal with the mapping between inertial frame and body frame, the velocity coordinates between inertial frame and body frame. So as per the kinematics, if you start with kinematics, you will have a mapping between the velocity rates eta dot would be j of psi times zeta. So this is the mapping between velocity rates in the inertial frame and the body fixed frame. And we also have the dynamics in parallel. So the dynamics expressed with respect to the body frame would be tau. The force vector tau would be d of zeta dot plus n of zeta. So where D is your mass matrix with respect to the body frame, you are required to find out the mass matrix with respect to the inertial frame. So I label this as equation 2. So yeah, we in the dynamics term we have a zeta dot component, and in the kinematics we only have a zeta component. So if we differentiate equation 1, sorry, differentiating 1, we would get eta double dot would be j of psi zeta dot plus j dot of psi zeta. So from here, what would be zeta dot? Zeta dot would be eta double dot minus j dot of psi zeta, and we have to pre-multiply this with j of psi. Sorry, I'll make this more clearer. Zeta dot would be eta double dot minus j dot of psi zeta. This entire expression pre-multiplied by j of psi inverse. I'm labeling this as equation 3. So I am straightforward substituting equation 3 into the dynamics equation. So equation 3 in equation 2 would give you torque. Tau would be d of psi. Zeta dot would be j of psi. Yeah, j of psi inverse. Eta double dot minus j dot of psi zeta plus n of zeta. This is your equation 4. Right? I hope this is correct. J of inverse zeta double dot. Okay. So for the time being, we'll leave equation 4. Sorry. Yeah, for the time being, we'll equation 4 as such. Right? And again, we have one more variable here, tau, that is to be refined. We need to transpose tau in terms of F, or the components of forces in inertial frame of reference. But here the torque means the force vector with respect to the body fixed frame. So again, if you recall the conservation of power, from conservation of power, this would be J transpose. Sorry, what is basically conservation of power? Tau transpose zeta would be F transpose eta dot. This is simply equation 5. So what does this equation means? It simply states power in body frame is simply power in inertial frame. Power is simply a scalar quantity. This is the tau transpose zeta is simply a dot product of tau vector and zeta vector, and F transpose zeta would be a dot is simply equivalent to the dot product of F and eta. So since power is conserved, power doesn't really change if you are simply transposing it from one frame to another. So power in body frame is basically equal to the power in fixed frame or inertial frame. It doesn't change regarding to what frame that you are expressing. So with this in mind, again, from kinematics, what is eta dot? From kinematics, from equation 1, eta dot is simply j of psi into zeta. So tau transpose zeta would be F transpose j of psi times zeta. So zeta and zeta get cancelled. So if we take transpose throughout, you will get tau would be J of psi transpose F. This is equation 6. So yeah, I think we now have all the ingredients. So if we substitute equation 6 all the way to equation 4, I hope it is visible. If it is not visible, please let me know. So if we substitute the tau in the left-hand side of equation 4, what would equation 4 look like? 6 in 4 would make equation 4 as J of psi transpose F equals D of theta J of psi inverse eta double dot minus J dot of psi theta plus n of theta. And F is simply, if we take this J, if we take this J of psi transpose to the right hand side, how would your F matrix would look like? F would be J of psi inverse transpose D of zeta J of psi inverse eta double dot plus some other terms, so and so. So basically, your inertial matrix or your mass matrix is just your the coefficient of the acceleration vector or eta double dot vector. Right? If you're writing the equation with respect to the body frame also, if you're writing the equations of motion with respect to the body frame, this over here, this is your acceleration vector zeta dot, and the coefficient of this acceleration vector is your mass matrix. And if you are writing this entire equations of motion in terms of body fixed frame, this is the coefficient of acceleration vector, where eta double dot is the acceleration vector in inertial frame, and this is the coefficient of acceleration vector in inertial frame. So in that regard, if you are given D, then what would be D of eta? D of eta would be simply the final expression that we have derived. I hope the space is sufficient. Yeah. If I'm simply taking this D of eta outside, I'm writing over this space. Okay. So D of eta would be J of psi inverse transpose D of theta J of psi inverse. This would be a mass matrix in inertial frame. Right. So if you do that, you are given the Jacobian matrix also. So in the question, it says the robot is oriented at 60 degrees with respect to the x-axis of the inertial frame. So what would be your Jacobian matrix look like? Your Jacobian matrix J would be cos 60 minus sine 60 0, sine 60 cos 60 0 0 0 1. This would be your Jacobian matrix. So you have all the ingredients. You have the Jacobian matrix. You have the Jacobian matrix over here, and you also have this expression for the mass matrix or the inertial matrix in inertial frame. And the question also gives you the D matrix, the mass matrix in body frame also. So if you multiply all this out using this expression, if you use this multiplication with all these known terms, you will, I suppose you will end up in option 2, option B, this option. Again, another way to eliminate some other options would be to see if the matrix is symmetric. So as you might know, mass matrix is always going to be symmetric, irrespective of what frame it is referenced to. So option 3, you can obviously eliminate it because that is not symmetric. Option D is basically symmetric. Option E also you can eliminate because that is not symmetric. The final option is also you can eliminate because again that is also not symmetric. So out of the remaining 3 options, this would be your correct answer if you correctly apply this final transformation. So we moved from kinematics to dynamics. Then we have also applied the conservation of power. So multiple transformation across kinematics, dynamics, and conservation of power. We'll end up with the final expression for the inertial matrix. So I hope no one has any dispute in this regard, in this question. We'll check the answer. Yeah, as per the answer, the correct option is option B. And the correct expression, the right expression for this mass matrix in inertial frame would be J of psi inverse transpose D of zeta J of psi inverse, where J of psi would be cos 60 minus sin 60, 0, 0, sorry, sin 60, cos 60, 0, 0, 0. And D of theta is given in the question also. Okay, so moving on to the next question. Okay, again, this is similar to the question that we have seen earlier. So a wheel configuration matrix of a mecanum wheel is provided. So if the vehicle needs to move in a forward or longitudinal direction, then what would be the individual wheel forces? So if this is a mecanum wheel, again, roughly reproducing the frame, this would be a longitudinal direction. Longitudinal, left side, right side. So again, we'll go forward with the most intuitive solution. All 4 wheels have positive F component along the longitudinal direction. So we'll try that out. 1 by root 2 times 1, 1, 1, 1, 1, negative 1, 1, negative 1, L minus D, L minus D, minus L minus D, minus L minus D. So if all 4 forces are equal and are all in the same direction, we'll end up, if you multiply this throughout, we'll end up with F plus F plus F plus F. Second component would be F minus F plus F minus F. Then F times L minus D plus F times L minus D minus F times L minus D minus F times L minus D. So this would be a constant in X direction, 0 in Y direction, and 0 along Z axis moment also. So our requirement is we would want the robot to move along the forward direction, and our vector, the force vector Fx, Fy, Mz is obtained as a constant along the first component and 0 along the remaining 2 components. So again, this is exactly as per the question's requirement. And this turned out to be the right combination of forces also. So again, that corresponds to option 1. All the 4 forces are positive Fs, and that too along the longitudinal direction. Yeah. I hope that is clear. Again, a similar question. Yeah, it is exactly opposite to the case that we have already seen. Now the question specifically says if the vehicle needs to rotate in counterclockwise direction. So I think earlier, what case did we see? Earlier, we have already seen minus F minus F. I think earlier we have seen this case for the clockwise rotation. So in case of a counterclockwise rotation, it would be a simple flip of directions. That would be F minus F minus F. We would simply try this out. So if the vehicle is to rotate in counterclockwise direction, we would want our force vector to be 0 along x-axis, 0 along y-axis, and a positive constant as a moment along moment about z-axis. So 1 by root 2 times 1, 1, 1, 1, 1 minus 1, 1 minus 1. We would simply use a constant, maybe q for L minus d, q minus q minus q. And the option that we are interested would be this one, f minus f minus f. We'll see that. F minus f minus f. So if we simply multiply this out, we'll end up with first row would be f plus minus f minus f. This would be f plus f minus f minus f. Second row would be f minus f minus f plus f. Third row would be q times f plus q times f plus q times f plus q times f. So this would be of the form 0, 0, some constant along z-axis moment. Again, this is exactly the form that we require. And this is exactly what the question demands. So our right choice of answer, our right choice of individual wheel forces would be this one, f minus f minus f. Or in that regard, option B would be our choice. Yeah, option B is our choice. Okay, so now we are changing the configuration. Now we are dealing with a 3-wheel omni drive. So since we haven't covered omni wheel in this tutorial, I'll simply reproduce the configuration. So as per our lectures, throughout the course, we have been using a mechanism wheel of this configuration. Oh, I think I made this. So yeah, this is the body fixed frame, x-axis, y-axis. The first wheel, second wheel, and third wheel. So all the 4 wheels are oriented 120 degrees apart. So this would be a left side, this would be a right side, and this would be the longitudinal direction. And this is the lateral direction. So yeah, our question basically asks if the robot is to move negative lateral direction, or it also says rightward. So we would want the robot to move in this direction along the negative y-axis. Right. So what would be the right wheel velocity combination? So if this is how we want the robot to move, then how would our force vector look like? Our left-hand side vector should look somewhat like this thing should look fx, fy, mz should look like 0 along x-axis, some negative constant along y-axis, and 0 along. Yeah, 0 for the moment along z axis. This is how our force vector should look like. So then what combination would give you the right, what combination would give us the right choice? So again, we will have to evaluate each of these options. So reproducing the wheel configuration matrix, 1 minus 1 by 2 minus 1 by 2, L, L, L. So yeah, what about the first option? It says F, F, F. Option 1 says F, F, F. So if we multiply this throughout, we'll have first row to be minus root 3 by 2 F plus root 3 by 2 F. Second row would be F minus F by 2 minus F by 2. And third row would be FL, FL plus FL. And this in turn would be 0. First row would be 0. Second row would be again 0. Third row would be 3 times FL. So again, this is not the case that we are looking for. We want 0, negative k 0. But here this would be 0, 0, some positive constant along the Z mode. So again, that is not the case we want. And what would be the second option? Second option also says F, F minus F. F, F minus F. So if we again multiply this throughout, what will happen? This would be minus root 3 by 2 F minus root 3 by 2 F. Sorry? Anything? Anything you wish to share?
No, sir.
Okay, okay. So again, if you consider the second option, you will have a quantity in the first component. You will have a negative quantity along the first component. So again, that is not the case we are looking for. We would want a 0 at the first and the third component. So here we already have a negative. We already have a non-zero component for the first entry. So again, we can straight away rule out this choice also. Option 2 also we can rule this choice out because we would want that to be 0, but we have a non-zero entity. And the third case is negative F, F, F. Third case is negative F plus F, negative F. So if this is the case, if we multiply this, what will we get? Minus root 3 by 2 F minus root 3 by 2 F. Again, we also, for the first entity, we have a non-zero entity here also. So again, we can rule out option 3 as well. We are ruling that out. What about option 4? Option 4 says F minus F, F. So that is simply a flipped sign of option C. So again, we can rule this out because both of these are simply flipped. And what about option 5? Option 5 says 2F minus F minus F. So the first wheel will have 2 times of F, and the second wheel will have half of the first wheel's traction force. So this is the first wheel, this is the second wheel, and this is the third wheel. So if you multiply this out, what will we get? The first entry would be, the first row would be root 3 by 2 times F minus root 3 by 2 times F. The second entry would be 2F plus F by 2 plus F by 2. And the third entry would be 2FL minus FL minus FL. So this would be 0. This would be 3F, and third entry would be 0. This is almost similar to the case that we want. But again, if you see the case, if you see the sign here, this is a positive term. This is a positive component. we would want our component to be negative because the robot should be moving along the negative y direction. As per the question, it should move along the negative direction. So yeah, we have already found out the right combination of forces, but we still haven't found out the right sense, the right direction. So if we simply flip these components, what will happen? If we simply flip the sign of these components, so the first term would be negative 2f, second term would be plus 2f, third would be plus 2f. Simply, if we simply multiply this out, first entry would be first entry would be 0 minus root 3 by 2f plus root 3 by 2f. Second entry would be minus 2f. Is it correct? Yeah, minus f by 2 minus f by 2. And the third entry would be minus 2f plus f 2fl plus fl plus fl. So again, simplifying, this would be 0. Minus 3f, second component would be minus 3f, third component would be 0. And this is exactly what we are looking for. Right, so our right combination would be minus 2f, f and f. Our right combination of wheel forces would be minus 2f plus f plus f. So in that regard, our correct option would be option. The final option, yeah, option E. Yeah. Yeah, that is the correct option. So yeah, again a similar problem. Again, we have been given a wheel configuration matrix for the 3 omni wheel drive. And we are required to find out the forward motion, the longitudinal motion. So if this is the robot, and this is the frame of reference, x-axis, y-axis. This would be the first wheel, second wheel, and the third wheel. Sorry. First wheel, second wheel, third wheel. And we would want the robot to move along positive x-axis or longitudinal direction. So yeah, we'll again see what would yield the correct answer. Minus root 3 by 2, root 3 by 2. We're creating the configuration matrix. L, L, L. And if the robot is to move along the longitudinal direction, how would we want the force vector should be? If the robot should move along the forward longitudinal direction, we would want the force vector to be of this form: a positive constant along x-axis, 0 along y-axis, and 0 moment along z-axis. This is how we would want the robot's force vector to be. And we'll simply eliminate, instead of going through all this option, we'll simply eliminate some of these non-intuitive options. So if we want the robot to move in a longitudinal direction, we would essentially want this wheel to be not rotating. Right? If this wheel is rotating, then the robot will have a component along y-axis. So if this wheel is not rotating, it won't have any component along y-axis. So we will basically eliminate all the options that has a component along the first wheel, and we'll shortlist the options having zero force along the first wheel. We'll basically shortlist these two options so that the vehicle can move along longitudinal direction. So going by the second option, it'll be 0 minus f plus f. So if you multiply this out, what will we get? It'll be root 3 by 2 times f plus root 3 by 2 times f. The first row. The second row would be 0 plus f by 2 minus f by 2. And the third row would be minus fl plus fl. So on simplifying, this would be 2 root 3 f by 2. Second row would be 0, third row would be 0. And again, this is exactly how we want our force vector should be. A positive constant along the first component and zeros along the other two components. Right? So in that regard, what is the correct option? It should be option B. 0 along the first component, minus f along the second component, and f along the third component. Yeah. Option B is the correct answer. And I guess this is the final question. Again, we'll go for this omni wheel robot. Body fixed frame, X, Y. This would be the first wheel. This would be the second wheel. This would be the third wheel. First, second, third. And the question says the wheel configuration matrix of a 3 omni wheel drive is given. And if the vehicle needs to rotate in clockwise direction, then what would be the individual wheel forces? So clockwise rotation. So if the body fixed frame is given, clockwise rotation would be, clockwise rotation would be in this sense. Sorry, clockwise would be in this sense. This is the clockwise rotation. So if you want to rotate the robot in clockwise direction, what will be the forces? What should be the forces? So purely going by intuition, the force vector should be, all the force vector should be in one direction, either along this direction, this direction, this direction. So if we apply a tractive force along this direction, everything is basically continuous. Or it could move in the other direction also. It could be going like this, going like this, going like this. So in essence, all the three forces should be equal, but we don't know the sign. Either all three forces should be equal and positive, or all three forces should be equal and negative. Yeah. And if you are going purely by intuition, we can eliminate a lot of options, because option B has a 0, and it also has a mix of signs. Option C has all forces to be equal and all the forces have same sign. Option D has a mix of sign. Option E has a 0. Option D has a 0. Yeah, and option F has a different magnitude. Option A also has same sign and same magnitude. So we'll shortlist option A and option C. All the other options are basically having a mix of units or a mix of sign or a 0. So again, if we simply do the matrix multiplication. So before that, how would we want the force matrix to be? We would want the force matrix to be 0, 0, a negative constant along the third component. Because the robot is rotating in the clockwise direction. If it is clockwise, we would want a negative constant. If it is counterclockwise, we would want it to be a positive constant. So if you are multiplying this matrix throughout, minus root 3 by 2, root 3 by 2, 1 minus 1 by 2, minus 1 by 2, L, L, and L. So if you are going by the first option, where all three forces are positive Fs, if you are multiplying this out, what will we get? We'll get 0 minus root 3 by 2 F plus root 3 by 2 F. And the second row would be F minus F by 2 minus F by 2. And the third row would be, FL plus FL plus FL. So this would be basically 0 in the first row, 0 in the second row, 3 times FL. But we have a positive constant for the third row. So yeah, in this regard, it's almost similar, but we would want a negative sign because the question says clockwise direction. We have a positive constant here. We would want a negative. We would want a negative constant at the third row. So if you want to get that, we would have to flip all the signs. We would have to flip all the signs of individual wheel forces. First force would be negative F. Second would be also negative F. Third will also be negative F. So if we again multiply this out, this would be root 3 by 2F minus root 3 by 2F. The second row would be minus F plus F by 2 plus F by 2. Third row would be minus FL minus FL minus FL. So on simplifying, we would get 0 for the first component, 0 for the second component, minus 3 times FL for the third component. And this is exactly what we are basically looking for. We would want the rotate to be rotating in counterclockwise direction. And if we have all the forces to be equal in magnitude, but of this negative sign, all three forces are minus F, minus F, minus F, we would end up, our robot would end up rotating about its own axis in the clockwise direction. So in that regard, our second shortlisted option, option C, would be the right answer. Option C. Yes, option C is the correct answer. Actually. Yeah, so the thing is that like this would be the exact sort of questions that you can expect for your assignments as well as for your end semester exams. Most probably you won't get any surprises. So yeah, I think we have reached the end of the session. You can expect similar sort of, I hope the deadline is not finished. Deadline of assignment 3 is not over. Murali, could you confirm whether is it over or is
it is?
Is it ongoing?
It's finished.
Oh, it's finished. Okay.
The 15th.
All right. So assignment 4 is going on as of now.
Yes.
Okay. I think our schedule is a bit offset by, this is basically intended to help learners to solve the assignments. So I guess we are delayed by a week, I guess. The problem solved. So anyway, like if people are not getting proper answers for these assignments, maybe they can use this for finding the answers, or it could be useful for their final exam also, the final certificate exams also.
Yeah.
So I hope this is fine, right, Murali?
Yeah, it is okay.